Thank you very much. It's my pleasure to give the talk here on sensing with Wi-Fi, theory, practice, challenges, and limits. Before I start the talk, I'd like to express my full appreciation and also the acknowledgement to the great efforts and hard work from my PhD students and research fellows who have significantly contributed to the research that I'm going to talk about later. So with that, let me move on to the talk. So Wi-Fi sensing is actually belongs to the category of radio frequency sensing. Also, we call it RF sensing. The rationale behind the RF sensing is very simple, that we transmit the wireless signal, and we detect the signal reflected from the environment, right? Like what is shown here, from the object, moving object, human beings, etc. And by detecting the reflected signal, we are able to sort of get information about the environment. And by that, we can detect any dynamics from the environment, and infer any activities going on in the environment. And Wi-Fi sensing has been used for many applications, including human tracking, human-computer interface, vital signal monitoring, health caring, security system, etc., etc. Right. A specific nice feature about Wi-Fi sensing is that it's contactless, right? So people doesn't have to wear any device, and there is no dedicated sensor, and the sort of the coverage of the sensing is very wide. Specifically, it can actually be used for detecting non-cooperative objects, right? Doesn't like, well, in a typical wearable environment, you need the subject that you want to sense about to wear sort of devices. Using Wi-Fi sensing, we can detect any non-cooperative object as well, like in the security applications, right? Having said that, it seems a little bit odd, right? And talking about the nice features of no need of wearing anything in the wear-assist workshop, right? But I do believe that the Wi-Fi sensing, or more broadly speaking, wireless sensing, is complementary to wearable systems. In terms of the flexibility of the system deployment, and I do believe integrating the two types of system will actually envision more application, and also ease the future development of systems for more applications. Right? Okay, so let me give you one example. Actually, this is one system that we have recently been studied in NTU. Right, this is we are using the Wi-Fi for detecting human activities, right, in the room. And you can see that this is in the NTU open house testbed, where we have a room and we are using the Wi-Fi signal for detecting the human being inside the room. And you can see that from the camera view, right? We know that, okay, how this person is moving, but we are not using any information from the camera. And we are solely based on Wi-Fi, and we can detect whether it is moving or standing still. And more importantly, we are trying to catch this sort of critical fall of human being. And you can see that after we detect the falling, and we will be able to trigger alarm. And this is particularly important for healthcare, especially for the aged groups. And there have been a lot of other applications proposed recently in the research community, including like the work from MIT in detecting moving objects beyond the walls, and the work from Washington in recognizing the activities of human beings and also the gestures by Wi-Fi signal, detecting of the human breathing and heart rate by Wi-Fi, even the emotion recognition using Wi-Fi, right? And the sleep quality monitoring and the human posture estimation, right, based on solely Wi-Fi signal. And recently, there have been a lot of startup, commercialization efforts that tries to bring this technology to more productization, right, in industry. And you can see many emerging startup companies trying to build system around Wi-Fi for motion detection, activity recognition, critical health status monitoring for human beings, etc. Right. So I guess here a very basic question, especially for the community in VRCs, right? Especially for those who haven't done research in this area, maybe a very fundamental question is, okay, why Wi-Fi sensing is possible, right? What is the magic behind it? Let me start with a very simple example, right? Where you have a transceiver, right? That is your mobile device that tries to transmit through Wi-Fi to the AP, right? Like what we show here. And we have an environment where we have obstacles, we have moving objects, human beings around. What happens is the transmitted signal doesn't just go straight to the Wi-Fi AP, but actually propagates through different paths, which might be direct line of sight paths or other paths reflected by the surroundings, okay, like shown in this figure, right? There are, I mean, let's make it very simple. Suppose there are only 4 different paths, and then what you get is really the superimposed signal. That's a signal from different paths adding together, right? Here, okay. And suppose we are sending some modulated signal, then what we are getting here is an add of different copies of this modulated signal here, right? If your modulated signal is complex itself, then the superimposed signal is also very complicated. But let's make it very simple. Suppose we are transmitting a very simple signal that's a single tone, right, of a frequency f, okay? And let's use a basic trigonometric expression, and we can use a more complicated, I mean, complex exponential for math works, but here let's make it very simple. Suppose we have a very simple frequency f signal transmitted from the mobile device. And what happens here is when the signal propagates through different paths, it may attenuate, and also because of the transmission distance shifted in time with different effect, okay? So from the first pass, it may be attenuated by alpha 1 and then shifted by theta 1. And for the second pass, it's attenuated differently and time shifted differently. And then at the end, where is the receiver, when they add up together, what do we get? If you haven't forgotten what you have learned in signal and systems, then a very simple answer is yes, you get basically the signal of the same frequency, right? That is also 2 pi ft, but with a different attenuation factor and a different shift. Okay, that is a super imposed signal of the same frequency components from different paths. Okay, what you get actually can be parameterized by the attenuation and its time shift. Okay, then suppose we are transmit signal with a bandwidth here, right? Now we have multiple frequency components. Then what you can get here is multiple different parameters for this attenuation of that frequency component and time shift. And it's different across different frequencies because different frequency signal has different wavelengths, and the same propagation distance may result in different attenuation and time shift. Okay, that's the basics. And then, but from this example, right, you can see very clearly that the superimposed signal can be parameterized, and the parameters about those different frequency components do tell you something about the environment, because different environment has different multipath profile. Okay, those different paths may be different, and as a result, you may have different parameters at the receiver side. Okay, and then reversely, using those parameters, it gives us opportunity to recover sort of information about the environment, and that is the basics of this Wi-Fi sensing. Okay, then you can imagine an environment where you have some objects moving. For example, in this case, this person is moving around in this room, and the particular propagation path related to that person is varying across time, right? And as a result, what you get at the receiver side, the parameter about the channels will vary as well. And if we can sort of associate those parameter variation to the moving objects, then we can sort of recover what is the dynamics of the environment. And by that, we can sense sort of different activities from the human being. Okay. this idea actually has been practiced for many years. Okay, 20 years ago, right? People have been using this idea for radio frequency localization. Okay, the basic idea is, okay, now the environment, let's suppose the environment is not changing or not changing very fast. Instead, the transmitter is moving around and we want to sort of locate the transmitter itself. Then what happens is the movement of the transmitter will also result in the dynamics of those propagation paths. And as a result, if we look at them as a whole, we see attenuation of the signal. Okay, the signal strength received at the receiver side may vary. And particularly, we can see, statistically increased signal strength when the transmitter moves towards the receiver and decreased signal strength when the transmitter moves away. Okay, that is a basic idea. And that is a very rough utilization of this idea. And that has been done 20 years ago in many systems, like the radar system, which is built 20 years ago by Microsoft for using Wi-Fi for locating the transmitter. Okay. And the landmark, which was built for locating the RFID tags, okay, by looking at the signal strengths. And as you can see in those examples, right, they were pioneer applications at that time, 20 years ago, but they were making use of the RF in a very rough way, right? They are looking at combined signal strengths, not a detailed components of different signal propagation paths. And that is also limited. That was also limited at that time by the hardware that we had. Okay. And most recently, actually, we have seen that the Wi-Fi standards, recent standards like 802.11n, AC, or the rolling out AX, they require so-called channel state information, okay, for transmission purpose. And then what is a CSI? Basically, that is associated with the modulation scheme, right? We are moving from modulating the whole signal within the band to cut the band into small pieces and modulating signals separately in those we call subcarriers. And as a result, we need to have those channel coefficients for different subcarriers, and we call them CSI. Okay, and the CSI was proposed and used for communication purpose, but we see it as a very detailed and informative way for us to learn the environment dynamics. Okay, compared with what we did 20 years ago using signal strings, using CSI is more like, okay, we have a more detailed and specific view of how different frequency components are affected by the channel. And by looking at those different frequency components in a combined way, we can sort of recover as much as possible details about the environment. Okay. That is a core idea behind. And if let's go back and look at this example. Now we have a transmitter and now we have a receiver. Suppose they are not moving, static. The environment is truly changing, and especially this person is moving around. Okay, what we have is, let's suppose we are transmitting a signal XT, and the channel is, the propagation channel is quantified as a HT, and then at the receiver side, what we get is really the convolution of the channel and the transmitted signal, right? This HT convolves XT, right? And what we get in frequency domain is actually the channel in frequency domain, that is frequency domain received signal divided by the frequency domain transmitted signal. Okay, and the HT basically is the CSI, right? Telling you the different channel coefficients on different frequencies. Okay, and maybe this is a little bit abstractive, and let me use a more concrete example to show this point. Let's suppose we have a transmitter here and we have a receiver here. And when the transmitter is transmitting signal, and the signal starts from time 0, and it propagates through different paths, as you can see, right? It propagates through different paths and reflected by different components, and as a result, they were received at the receiver at different time. Specifically, we have 4 time beams that we receive the 4 copies of the signal, okay, reflected by through different paths. And specifically, we call this power delay profile because you're receiving the power at different delays. And we also call it impulse response of the channel. It's pretty much like when you have an impulse as an input, then what do you expect as the output, right? It's like when you have an input like pong, right? What you hear is like pong, 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 right? This is the impulse response. And that pretty much tells you how many paths we have and how far away they are from the TX to the RX, okay? And specifically, this channel impulse response is sort of associated with this CSI, that is the channel frequency response. And actually, they can be translated to each other. Okay, they are basically talking about the same thing. That is the channel itself. So the impulse response can be easily translated into the frequency response and vice versa through FFT or IFFT, right? So now we have the CSI from the Wi-Fi, and as a result, we can and we should be able to recover the power delay profile. And that tells us roughly the idea of how many paths we have and how long roughly are they, right? And now this is just a signal from one antenna. And now suppose we have multiple antennas, then as the figure shows here, one signal, when you receive it from different antennas, and you can tell that they traversed different amount of distance, specifically, right, this small delta here. And that is related to the angle of the arrival of the signal. And by looking at this small delta and comparing across different antennas, we can precisely recover the direction of the incoming signal. And that is called AOA, angle of arrival. And when you have more antennas, you can have more resolution for this angle of arrival. And suppose we are equipped with multiple antennas, and that is the case for current commodity Wi-Fi, then we are able to sort of recover the direction of the reflected signal, especially if we can extract that signal path and isolate it from other paths, we may be able to track the movement of the reflector, right, of that path. So now this is basic, right? We have the sort of spectrum analysis, and we can recover the different paths, and we have multiple antennas. We can sort of detect the arrival of the signal, the angle of arrival of the signal. Right? By combining the two information, we can actually track, right, the reflectors. Okay, and there are typically two different ways to sort of utilize such information, and we can build explicitly signal propagation model, right? We can build a wireless propagation model, and we can estimate the channel parameters like the angle of arrival, time of flight, angle of departure, Doppler effect, etc. And then they will give us signal paths and their dynamics for tracking purposes. Or we can go the other way where we build machine learning models and we use CSI because we know that they characterize the channel on the wireless channel, and then we can map sort of CSI variations to infer different human motion, location, or activities. Right? There are two different ways of using such information. And here I want to give another example where we built a system for detecting the human hand movement. Okay, in this case, we are using commodity AP here, and we are using two pairs of antennas to detect the reflected signal from human hands, so we can allow the hand movement in the air and let the human being write in the air and recognize the handwriting. Sorry. I'm not sure if you can see the video here. And in this case, we use the reflected signal to track, okay, the motion of the hand movement, and then map that into a figure, right? It's an image, and then input it into a convolution neural network for handwriting recognition. Right? And the good thing about it is you don't have to wear anything again. This is a very lightweight way for sort of human-computer interaction, and it can be easily adapted to different human subjects, as the video suggests, even when they are having different writing styles. As long as we can accurately track their movement, we can translate that into an easy handwriting recognition problem, where we can build very mature machine learning model to recognize those handwriting. Right, so this figure shows a basic rationale of the system where we use a Wi-Fi front end for detecting and extracting motion trajectories, and then use the machine learning model for recognizing those trajectories. Okay. Specifically, this is antennas, and we're detecting the reflected signal from the moving heads. And based on that, we figure out potential candidates of moving trajectories. And then we input that into the as images to existing machine learning models and try to recognize different handwritten characters. And the particular nice feature about this system is we can easily sort of switch the handwriting applications across letters, digits, or even Chinese characters by supplying different handwriting training data sets. And we don't have to rebuild the training data sets because they have been well studied in the handwriting domain. So by simply supplying them to our system, we can get a plug and play effect, and we can accurately recognize those different input in letters, digits, or Chinese characters. Okay. Right. Having said so much about the nice features and applications of Wi-Fi sensing, right? Maybe a question that you have in your mind is, it's so magic, and is there any limit, right, in using wireless sensing? And my answer is yes, it is limited, and it's very much limited, especially by commodity devices. Okay, so there are two major diversity that we export for Wi-Fi sensing, and they are also sort of limiting the performance of our current existing Wi-Fi sensing systems. The first diversity is the frequency diversity. Okay? And this is easy to understand. Basically, when you are using a wider frequency spectrum to observe the signal, then you are getting more alpha and theta, right? If you can remember, we are getting more parameters for more frequency components. And that provides more information for us to recover the wireless channel, and that is the environment, right? If we have limited bandwidth to observing the wireless channel, then we have much lower resolution in telling the difference or dynamics of the environment. Okay, that is a fundamental limit. And in typical Wi-Fi devices, we are limited by that to 20 or maybe 40 megahertz, okay, in different frequency range. And the other limit is spatial diversity. That is a number of antennas you have, because you have to separate the antennas far away from each other so they give you independent observation of the signals. And the number of such independent observations allows you to have a better resolution in telling where the signal is coming from. Okay, and current Wi-Fi devices have limited number of antennas, and that also limits your resolution for AOA. Right? So we have been doing some research in recent years, particularly to improve the diversity with commodity Wi-Fi hardware. Okay. And that provides a general platform for all of those Wi-Fi based sensing applications. Specifically, one is for improving the frequency diversity, and that is a splicer, which was published in MobiCom 15. The other is to increase the spatial diversity through extended antenna arrays, which is called SWAG, published in MobiCom 18. I'm not going to the details of the two works, but I will introduce rough ideas behind. So the key idea of splicer is that, okay, while our Wi-Fi transmission is limited in a certain bandwidth, that is 20 megahertz or 40 megahertz in 5G range, but the total frequency range allocated to Wi-Fi is not limited to that. For example, in 2.4 gigahertz, we have 80 megahertz, and in 5 gigahertz, we have even 200 megahertz total bandwidth. That allows us to sort of probing the channel multiple times and then adding up the observations. Okay. Simply speaking, that is, okay, we do transmission at different frequency bands using different packets and later combine them together to get observation of a wider band. Right? The idea is very simple and looks very easy. The reality is the combination requires a lot of research and engineering efforts to remove sort of system and bias